Good day to you, dear audience, and welcome to Poly U and You, the online lecture series of the Polytechnic University. My name is Hoorn, Johan Hoorn, and I'm an interfaculty professor in the Department of Computing of Polytechnic University and in the School of Design. Today the lecture is about a very special social robot called Alice, and why she is so special and famous we will discuss today, and also what the science behind all that is. So who is Alice? Alice R50 is a small robot, 60 centimeters tall, manufactured in the US by Robotics and designed by David Hansen, who also created the Sophia robot, which is pretty famous at the moment. Alice R50 was engineered so badly that we demanded an extra Alice, a donor Alice, for spare parts, because we had to reassemble that whole thing, and we also had to redo the entire software just to make her run. Now, why is this Alice famous? She was the topic of a documentary about an observational study that we did with 3 older adults being visited by our Alice to keep them company. Mind you, these old ladies were very lonely, so they didn't have any other people around. These women became so attached after a few weeks to that machine that we really had trouble taking it away after the experiment ended. Actually, those people were more lonely than before because we took away her company. And that documentary went viral, as we say today. If you want to have a look at that documentary, there is a URL that I included in the slide where you can see the trailer, or you can, for a few dollars, see the whole documentary on Vimeo. That documentary gave us quite a bit of international recognition. Now people understood that robots can alleviate loneliness. So we went on film festivals in Paris, in Rotterdam, New Zealand, Israel. We were in museums. We were in London at the documentary festival there. And not only off the campus, of the university, beside academics, there was this recognition. Also within academics, and this was quite special. We made it to The Lancet. For those who don't know, that's the top 1 journal in medicine, and it's quite something that the medical people, the doctors, would be interested in a robot to, well, basically support people with mental problems. Now, what's the science behind all this success? Basically, most people would say, and I call them the believers in artificial intelligence, that behind that machine was, of course, something like, and now I'm going to use very complicated words, such as deep convolutional neural networks, and they did feature extraction in speech and facial expression for emotion recognition, after which the natural language processing system selected the appropriate emotional responses. Yeah. That may be the case, but that wasn't the case. So I'm not gonna bother you with the picture that you see at the bottom of my slide, where video data are slowly translated into a choice of an emotional expression. No, sorry to say, artificial intelligence, and now I'm gonna hurt people, I'm afraid, that was not where it begins. Artificial intelligence basically is where it ends, after you have understood how things work. And unfortunately, and again, I'm going to hurt my whole department here, many engineers think that AI will solve things on its own without them, the engineers and the scientists, studying humans first. And this is what I call the self-learning mistake of AI. And I know I will be countering a lot of people right now, but I will do it anyways. So if this wasn't the science behind Alice, then what was it? There were also a number of skeptics of the robot Alice and the AI, and they may think that Alice robot was just in remote control with a guy behind the curtains. So that was all a hoax. Humans talking to humans on the phone, as it were. And in human-computer interaction, we call that a Wizard of Oz setup, that somebody behind the screens is actually manipulating the robot, typing in texts after the famous fairy tale Wizard of Oz. So those people would actually tell us that people need other people, so study psychology first. And we need no machinery to fake friendship. That was quite some of the critique that we were facing. But I'm sorry to say again, all the psychologists, I will disappoint them, it's not where it begins. Psychology and other social sciences, such as communication science, they are intermediary, in between, after you have understood what you're actually dealing with. What is that thing, a robot? So unfortunately, many psychologists think that humans are the gold standard for human performance. But many humans do not think that other humans are doing so fine. Many psychologists think that robots are taken for real humans and should be designed as real humans, and many designers think that too. So again, I'm going to hurt a lot of people by saying this is a human-centered mistake of psychology and of most of design. Sorry. So then what is the science behind Alice? Well, perhaps quite unexpectedly, it is the humanities. The humanities, yes, because robots are fictional characters. They are not real people. And there are two disciplines in humanities who know exactly what the effects of fictional characters are, because they have been studying that for about 300 years. It's literature and is theater, and adjacent to that, film studies. Robots are not real people, and they are not treated as such. And this is where it all started with our Alice. Well, actually, robots didn't start with Alice. Robots started with humanities a long time ago. They were a philosophical idea at first. And you know where? That was in China. And they featured as fictional characters in our minds before they were made by engineers. And you know where? That was in China too. 2,500 years ago, we see the first record of somebody in the 3rd, 4th century before the Common Era creating a humanoid automaton for King Mu of the Zhao dynasty. We also have examples a little bit later, but still, I mean, we talk 200 years after the Common Era, that during the Three Kingdoms there was this south-pointing chariot with a differential gearbox. So the differential gearbox is no invention from the West, it's done in China. And the little man on top, the mechanical puppet, points to the south with every turn of the road that you take. So that thing is like a compass. You will always find your way back to the south. Third example, just a handful I give you here, is Su Song from Song Dynasty, creating a cosmic engine using mechanical puppets that would ring cymbals and bells to tell us the time. And that's in the time around the year 1000 that we were on crusades in Europe. So robots started with humanities, and literature and theater formulated for us the dimensions along which fictional characters are experienced, which are good versus bad, you know, good guys, bad guys. That's one of the principles of movies and stories. Beautiful versus ugly, and realistic versus unrealistic. Think of a more social drama, realistic drama, versus a unrealistic cartoon story. So if we apply that to robots, then we encounter good robots, such as C-3PO from Star Wars, who always is helping people, telling us, I'm programmed to understand humans. Well, if it only were be that way. And we have bad robots, such as Megatron from the Transformers, telling us the universe cowered once at the name of Megatron and it shall do so again. That's the bad robots that we see quite a bit in Hollywood movies, don't we? We have beautiful robots, such as Coppelia. Well, remember that name Coppelia because she will return later on in the presentation. Here we see a version by the English National Ballet. Coppelia is a dancing doll created by Dr. Coppelius, so real that a human man, Franz, fell in love with her and denounced his own fiancée, Swanhilde. Beautiful robot. There's also an ugly robot like this one, Robbie Robot. That doesn't mean that he is an evil robot. He helps damsels in distress, as you might see, but he's not like what you say, a good-looking guy. We have realistic robots, such as Data from Star Trek, and he's pretty realistic because he looks like a human. That's what we mean at this moment with being realistic, realistically looking like a human. And he has these desires to be human. I want to live, however briefly, knowing that my life is finite. You know, that's pretty human-like. Or there are still many human emotions I do not fully comprehend: anger, hatred, revenge. And we have unrealistic robots like this piece of art, the Tin Can Man. Yeah, well, it doesn't really look like a human, and I think it won't work as a robot either. So that's on the unrealistic side of things. So we have 3 dimensions that we learn from the humanities that should be visible, that should be there when people assess, experience what the robot is like. Good versus bad with an expensive word, we call that ethics. Beautiful versus ugly, which we call aesthetics. And realistic versus unrealistic, and we call that realism. There's another thing that we were learning from humanities, which is the word identification. Identification with a fictional character. Now later on you will see that the psychologist will break that idea of identification down into 2 components, but for now, identification in literature, for instance, is used to show the following. There is this example of Goethe's Die Leiden des jungen Werthers, the sorrows of the young Werther. And male readers started to dress like this man because Werther, it is an epistolary novel. He had an impossible love for Charlotte, who was already engaged. And he loved her so much, and he couldn't get her, that he shot himself because of unanswered love. And there were many readers dressing up like Werther, very romantic people, and then shooting themselves for the unrequited love, just like the protagonist. That's identification for you. You feel what the hero feels. Now, then we see how humanities evolves into psychology, because that whole thing of identification has 2 components, the psychologists say. It's similarity, it's being same or different, and it's being engaged, which has 2 components, which is being involved, friendly feelings, or feeling at a distance, cold feelings, not so friendly. Examples of similarity are, for instance, that there is this robot portrait created after a real woman by Hiroshi Ishiguro, and that's a similar thing, right? She looks like the person. We also see an example of engagement with the older adult holding a Nao robot as if it were her grandchild. She is engaged with that machine. So we have some kind of model right now. The things that we look for in a robot. It's ethics, good or bad thing. Aesthetics, how it looks. And realism, in how far does it resemble a human being. And we compare that thing to ourselves, similarity. And we have a feeling about it. That's what we call engagement, being involved and at a distance. So feelings, emotions, what are they? Now we are really entering psychology here. Emotions, according to the books, are tendencies to engage in behavior when, and this is very important, goals and concerns of someone are at stake, whether you are threatened or supported. So emotions are goal-oriented. If you have hunger, then a knife in a cabbage That feels fine because we're going to eat now, you know. I have positive emotions because something good is going to happen. I am achieving my goal of being fed. But what about this? Now, it's not so nice anymore because there is this similarity of that wooden thing. It's not living, but we identify with that wooden thing as if it were human, and we can empathize, you know, engaging that we have such knives in our heads, and the goals and concerns that are threatened now is that I would die from that. So I have negative emotions. If you want to put it in a picture, then our tears of joy and sadness, according to the psychologist, are based on two things. On the one hand, we can have warm feelings or cold feelings, going left and right, but there's also intensity to that emotions, how much water is flowing through the tap. And that's what they call relevance, the trigger of emotion or the intensity of emotion, and which way the emotion goes, warm or cold, positive or negative, that's what they call valence, the direction of emotion. These two things are the mechanism on which we are driving our emotional system. So if we put it back to our model of how do we experience a robot, then we look for ethics, aesthetics, realism. We compare for similarity, but we also compare what we see for relevance to the goals and concerns that we have. Is it a good guy, and is it relevant to my goal of achieving some task? And the valence that we have, do we have positive prospects of using that thing? Do we have negative outcomes that we expect for using that thing? And all that feeds into how we feel about it, our being engaged, involved, or at a distance, eerie, or oh, it's so cute. Then we had to return to human-computer interaction because a robot is interactive. It's not just a picture on a screen or a character in a book like we have in the Humanities. And so we see here Hanson Sophia, world-famous machine, talking to a world-famous actor, Will Smith, and Will Smith actually discovers that you can speak to her and that she can listen to you, and he can actually kiss her. You know, that thing has action possibilities. In human-computer interaction, action possibilities of an interactive system we call affordances. So Sophia offers the functionality to speak to her, offers the functionality of listening, like a chair affords you to sit on. Affordances, things you can do with the machine. Human-computer interaction also looks into other aspects. For instance, Will Smith here sees that I will perhaps want to see her again next time we go out. I have good use for this machine. Well, perhaps he wants her to do the dishes or something. In human-computer interaction, we call that use intentions. I want to work with that machine again, use intentions. So we took that too. And then, after all these things, people are really pleased with their new system, their new friend. And in human-computer interaction, we would call that being satisfied with your system. Then the question, of course, is Sophia pleased with her new user? That would be a question to AI, I suppose. Okay, let's see. If we put psychology, media psychology, yeah, so it's the psychology of using media such as film, literature, robots, and human-computer interaction. If we put them together, well, then you have 20 years of empirical research that we did leading to a model that's called interactively perceiving and experiencing fictional characters, or IPEFIC for short. I'm not going to go through that whole model and where all the arrows are leading. I will just confirm with you that after 20 years of doing studies with real people, we did find that ethics, aesthetics, realism, as well as what you can do with the machine, the affordances, are the things that people are looking for when they judge their robots. Then all that goes into how relevant is that, what I can do with the robot for my goals and concerns. For instance, is it relevant to teach me a language? Is it relevant for doing household chores? And what's the valence that I have? Do I feel approach or avoidance while I'm working with that machine? And then there's something like similarity between us. Is it more or less like me that has an effect? If the use intentions that come out of that are high, that feeds into satisfaction. At the same time, we are involved with that thing, having empathy, sympathy, warm feelings, approach tendencies. And at the same time, and this was really interesting, a result of our research, there is in parallel, not in opposite, but at the same time, the feeling of distance, such as antipathy or cold feelings, eerie, avoidance, creepy, that thing. All that feeds into a measure of being satisfied with your robot, or not. So media, psychology and HCI together, 20 years of research, can now tell us what went on in Will Smith's mind. Yeah, that's what's been going on in his mind, empathic. But then the question, of course, is what is going on in the mind of Sophia? That's the AI question to it all. Well, this. This is what the robot brain looks like. Empty. Nothing. In other words, we should turn to artificial intelligence. How do we give the robot a mind of its own? Well, our answer was, we take our empathic model that was tested on users, how they perceived their interactive characters in games, office assistants, virtual coaches, and use that model to implement it into the brain of a robot. If you want to know about empathic and how we came to all our conclusions, in the bottom right hand corner you will find interactive engagement with embodied agents. That's the paper that tells it all. So we took our model and translated it into computer code. We put ones and zeros to it. Yeah? So if the thing has high affordances, I can do all kinds of stuff with it, and is relevant to my goals, then perhaps I have high use intentions, and given so high use intentions, my satisfaction is that high. Those are more or less the reasoning systems that are behind the implementation of the empathic model into the brain of a robot. Now, realize that from then on, Alice or any other robot regards humans as fictional characters in their robot world. That's interesting, right? Next, that computer code was implemented as a virtual dating partner. Yeah, so we created an application. Hi, my name is Will. Well, actually, that's a joke. His name was Tom. But Tom was driven by our AI and then put into interaction with girls of about 22, 23, 24 years old. And the girls had to assess what Tom was thinking about them. Does he think I'm unfair? He thinks I'm pretty. I think he likes me. That kind of thing that you do when you are doing a speed date. Now, how could we validate our original model with this setup? In the following way. In one condition, we put Tom in remote control, handled by one of two boys that did the speed date with the girls. In the other condition, we used our AI, the implementation of our empathic model, to handle the behaviors of Tom. And indeed, Tom, this setup is an adaptation from the Turing test, where people look whether a computer performs so well that the users do not discern that they are talking to a computer and think it's a human being. So the girls filled out, after they were speed dating with Tom, they filled out our empathic questionnaire, and they were unconscious about diagnosing how Tom felt about them. So think like this. Tom has a module to assess ethics. Now, do the girls see Tom has that module for ethics? And yes, he thinks I'm a good person, so totally agree. Tom has a module to judge aesthetics. Yes, I see. He thinks I'm pretty. Tom judges the girls for use intentions. Do the girls see that he does? Yes, Tom wants to see me again. So Tom's evaluations, while thinking about those girls, are evaluating according to the girls evaluated. And that way we could determine whether the girls saw ethic modules running in Tom's head, aesthetics and use intentions. So the question was, if Tom is driven by human confederates, by human boys, or by our AI, is there the same outcome in the questionnaire results of the girls? Are they the same? For looking whether they are the same, these results, we used Bayesian structural equation modeling. I will not bother you with that, just for the people who understand what that is. And in that kind of statistics, we actually saw that what the girls filled out in their questionnaires for the human confederates pretty much overlapped with what they filled out for conversing with our AI by means of Tom. So basically we could conclude that our AI was pretty much not discernible compared to how people were responding to boys. And that actually means that our AI, the implemented iPerfect model, passed the Turing test. People do not see whether they talk to a real person or to AI when implemented right. So if you have our media psychology plus human-computer interaction and design and computing, you can actually design robots that simulate emotions in a way not discernible from real human beings. And if you want to know the paper that explains all that, then you should look into dating a synthetic character is like dating a man. We call this affective computing. Now, what the heck is affective computing? This is affective computing. What you see here is a publication of the mathematics behind Alice's emotional behavior. It is not deep learning and it's not neural networks, but it's logic, symbolic AI using fuzziness. People who are specialists know what I mean. The AI does not sort it out for us. We sorted it out for the AI and then have it behave that way. For those who are interested, the code of that thing is available on the GitHub. Software engineering is done in Ptolemy. So anyone who has the skills can work with this affective computing machinery. Now that we have that, what will be the next generation of robotics? Well, my answer to that is it will be quantum computing. That's what I think. We saw data from Star Trek, robot data, saying there are still many human emotions I do not fully comprehend, anger, hatred, revenge, and I showed you the metaphor of this tab going left, right, and up to indicate warm feelings, cold feelings, and intensity, relevance. But that's actually not the right metaphor, because data, my dear robot, an emotional system is not a either-or thing. It's not either cold or hot. People can feel love and hate all at the same time. So it's warm feelings mixed in with cold feelings. They are mixed emotions, ambivalence. Yeah, so valence is actually streaming in parallel, two things at the same time, cold and hot mixed. That brings us back to emotion psychology. Amygdala is a structure in the brain basically evaluating of everything that comes in is a threat or something you can relax by and, well, perhaps enjoy. Amygdala takes in two information sources. One is what we call affective input, which is basically emotional input. The other is reflective input, which is a parallel process. These things occur at the same time. And sometimes one source may overpower the other. So let's look at the brain picture on the right-hand side. At the bottom of that picture, we see the word stimulus. For instance, I see a robot. Then the red path, the red route that you see going through the brain, first enters the thalamus. And the thalamus is actually checking whether I have seen these things before. It has to do with memory. And that whole red path is the immediate experience of an emotion that you may have. So everything coming in, everything that you see and hear, always takes the red route. However, thalamus can also send part of that information through the frontal cortex. That's the blue route. And that's more like thinking, reflecting about your emotion, or regulating an emotion, or having ideas of how did they do that technically. So the red path is responsible for, oh, it's cute and eerie, I'm a bit scared, and the blue path is more about why do I feel that emotion. All that feeds into amygdala, and amygdala makes the decision to say, the external response we call that, I have warm feelings, this is friendly, or I have cold feelings, I feel distance, and mixes, ambiguity about it. So my point is, next-gen robotics will be quantum computing. Why? Well, conventional computers are not really parallel. They process information very fast in a serial way. And that is not a good representation of what happens psychology-wise. But quantum computers, they have this weird thing that they have the possibility to run information at two places at the same time. So information is not at one place, it's at two or three places at the same time. How they do that, we see later on in the slides. One instance of this kind of computing is from IBM, the quantum experience, that has a superconducting qubit, and I will tell you later what that is. A qubit is a kind of switch, and they use that to get information at two places at the same time. Now, why would it make sense for an organic brain to make use of such quantum phenomena? Why would you? Because you can just do things serially as well, right? Well, there is something to say for why you would want that in a brain. You don't have to copy information to many places in the brain. It doesn't have to be at one place in the visual cortex and then going to the memory, or copied to the limbic system and then going into the language center, etc. You do not have to keep track where all that copied information goes to. You need no register. You do not have to reassemble it from the register because it's processed as one unit in different places, and so it ends up as a whole in amygdala for the output response. Information through brains runs on electrons and ions. They are particles smaller than an atom. And those quantum fluctuations, they happen everywhere in nature. It's nothing special in that sense. It's a weird thing, but it happens a lot. So it would be very energy efficient for a brain to also make use of quantum phenomena in the brain process for information. And yes, you will see that it's possible to grow nerve cells over silicon chips and transmit information from the one to the other, because everything runs on electricity. Those are called biohybrid circuits. Now, how would a cell do that, make use of quantum kind of phenomena? The cell body contains the information. It has dendrites that receive messages from other cells. Then there is the axon, which is the information highway passing on all those electrons to the terminal branches of the axon, where we have synapses, and synapses actually push electrons into other dendrites going to new nerve cells. So here we have them. They have these connections here, but there's also a little gap between those connections, and that's the interesting part. There are, between two synapses, little gaps where the electrons and ions are pushed from the axon to the dendrite. Now, most of the time in high school, we were taught that electrons are like marbles, you know, little spheres, as we see also in this picture. But basically, modern physics tells us that electrons are more like chewing gum. They can take a more elongated space from one place to another, and we will perceive that as human beings as at two places at the same time. Now, what if we have one system of neurons going to the neocortex for reflective processing and one system going into the limbics doing all the emotional processing, and we have electrons that are superposed between the synapse pairs? Then we have information that is available in parallel at more brain locations. If that is so, we could model the amygdala mathematically as if it were a Bloch sphere. A Bloch sphere is a mathematical representation of a qubit. So I will tell you what a Bloch sphere is next. First, I will tell you what a qubit is. A qubit is a switch. It is telling us whether a system is in one state or the other. But the peculiar behavior of these subatomic particles that the qubit is working with is that it can be coherently at two places at the same time. And that's a weird property that allows us to process yes and no all at once without a contradiction. If you would speak German, Jein would be what this process could be about. Yes and no at the same time. So mathematically, qubits are often represented as a Bloch sphere. That's the sphere you see on the right-hand side. And on the next slide, we will see why that is a very convenient model of reality. And of course, that is not reality itself. We don't have that mathematics in our brains. Amygdala as Bloch sphere. On the left-hand corner, the bottom corner, we see deep thought. I tried to understand how they did it. That's the reflective side of processing, the x-axis. When we follow the x-axis to the top right-hand corner, we get into shallow thought. So that's the continuum. It takes little energy. I hardly thought about that. Then on the upper left-hand corner, we have negative valence, the emotions of being scared. And the y-axis continues to positive valence approach. I feel this thing is cute. All that leads into a decision for the limbic system being dominant, a fast and emotional reflex, or the other way around, a slow reflective response, the neocortex being dominant. And it's the red arrow that points out on the Bloch sphere what the responses may be. Over time, the red arrow may travel around the surface of the Bloch sphere, pointing out scary, deep thinking, I hardly thought about it, but I think it's cute, like this. I feel scared, the robot could say, but I gave it some thought, and so I want to get close. And this kind of ambiguity we can model in quantum computing way better than in conventional computing. So NextGen robotics, science fiction still. Star Trek Data says, Captain, I believe I'm feeling anxiety. It's an intriguing sensation, a most distracting, yeah, Data, I'm sure it's a fascinating experience, but perhaps you should deactivate your emotion chip for now. And what do you know? Data clicks with his neck and the emotion chip is out. Data, there are times when I envy you. But we are not working on science fiction, we actually want to go into science fiction. So in the future, Alice will be supported by a quantum computer, a robot brain, and we have that, and we are trying to build that right now in the Artificial Intelligence for Design lab in Science Park. That computer robot brain is fast in parallel processing, capable of dealing with ambiguity of the user, but also of the robot itself. So the computer may tell us I feel scared, and Alice yet says, but I still want to get close. Just like Granny says, oh, it's so cute, but also a little bit scary. And that's it for today. If you want to know more about the science behind Alice, please read all these references and you are up to speed. And I think it's time now to take